So I'm starting the course a little bit different than I have classically, in the sense that I'm just going to start with the problem of limits in here. Typically, I have spent a week doing pre-calculus, the start of Calculus 1, and no good comes of it. Because what I do when I review material is I focus on things that you guys don't know. So my typical outcome in Calculus 1 is to review things students don't know from pre-calculus. At the end of the first week, the typical class is terrified because I've only focused on what you don't know, right? So I think what's maybe going to produce a more harmonious outcome is if we just start with the new material. And what we'll do is, as we encounter topics in pre-calculus that you're rusty on, we'll talk about them then. All right, that's the way I'm going to do things in here. Now, the other thing is, when I do have the notes, the lecture notes posted for you guys, my first chapter and second chapter are actually like history, and then like an overview of everything in the kitchen sink in pre-calculus, right? I'm actually skipping those chapters in some sense. I'm going straight to the third chapter, which is on limits, and starting there. So we'll kind of dip back into chapter 2 and chapter 1 as it occurs to us, all right? So let's talk about limits. And so before we even talk about limits, we have to face the problem of calculus, right? The first problem of calculus is the problem of tangents, right? So what's a tangent? Well, the first thing you might think about with a tangent is the problem of, like, what's the tangent to a circle? If I pick a point on the circle like this, right? The tangent line is what? It's the line which just does what? It just touches the circle at that one point, and it just kind of bounces off, right? For what it's worth, that line happens to be perpendicular to the diameter, right? So that's a tangent. And we've studied those things, humans have studied those things since the time of ancient Greece, right, at least. Euclid's Elements are full of like theorems about tangents to circles and such. So that's a tangent line to a circle. How about a graph, right? What if we have a graph of a function? How to find tangent line to graph y equals f of x, right? What would that mean? How would we define it? Is it still, I mean, it should be a line, right? Surely. But should it just touch on the function one point? Like, how are we going to define a tangent line? We draw some examples. So maybe the graph of the function looks like this, right? And pick a point, right? Pick a point. Let's say at this one. What would the tangent line at that point be? The line where the tangent line, the point on the graph where the tangent line goes through is called the point of tangency, right? So what would I can tell you what it's not, right? Like, sometimes it's useful to say what it's not. That's not the tangent line, right? That's not what we mean. It should be kind of like that circle, right? It's that line which touches the graph, but just at that one point close to the point, right? I mean, like, how to say that, how to capture that idea precisely. I mean, I can see it, right? I'm trying, folks. You can see it, right? It's something like that, right? When I draw stuff above my head, it kind of gets tilted when I go away from the board and look at it. That should be the tangent line, right? Something like that. Let me make an easier one. How about this? At the top of this hill right here, what would the tangent line be? It's going to be a what? A horizontal line, right? So it should be like this. So how do we define that tangent line? Like, right? That's the question. let's say how to define the tangent line through, let's say, a comma f of a on y equals f of x. So, here's my function, graph of my function. Try that again. It's my graph of my function, something like. So let's say that this point right here is above A. So maybe you guys can help me. If I'm going to, I'll graph it, right? Like something like that, right? Let's give this a name. What do you want to call the function whose graph is the tangent line? I'll make a definition. The linearization of f at A of x equals, let's say, mx plus, well, I guess I could say mx plus k for the moment. That's still not what I want to say, though. Let me back up just a second here. Let's say that L sub f upper A is the function whose graph is the tangent line. What's the graph of a function? That's y equals the function evaluated at x, right? Like y equals LFA of x. Now this function is called the linearization of the function at the point, all right? And so it's a line, right? And how do we write the equation of a line? We want line with a comma f of a is point on line. So that means we could write L f upper A of x as equal to f of a plus m times x minus a. Do you guys know about the point slope formula for a line? Let me remind you for a second here. Just sidebar. If we knew the point like 2 comma 3 and is point on line, with slope 7, you could write y equals to 3 plus 7 times x minus 2. That would give you the equation of the line that goes through the point 2, 3 and has slope 7. So I'm just saying we could do the same with this linearization. It's the value at the point is f of a, and then we do the slope times m times x minus a. So if you look at this formula, oh man, see, this is bad. It's not your fault. It's my fault. I get too into the math. And fortunately, everybody's here, right? So just the people on the internet. We don't care about them, though. I'm just kidding. We care about them a little bit. Anyway, so if you plug in a, we get what? This is 0, and this is just f of a, right? So you can check that when we plug in x equals to a, we get back the point. That's one thing we want. So that's the point on the line, and it has slope m, right? So making the line go through the point, that's easy, right? But how do we define this slope? How do we define this slope for the line? Like, how do you get this slope m? How to capture this, Because that's really the problem. Anybody can take a graph, right? Pick a point on it and start drawing lines through that point. That's easy. Oops. Pride goeth before the fall. Let's see here. There. It's almost easy. But what's much harder is to pick out of that infinity of lines which goes through that point. There's just one of those, right? Maybe that's the tangent line. And how do we define that? Do you guys have any ideas? Well, how about this? We can introduce another concept called the secant line. What's a secant line? You're fine. It's okay. So the secant line from x equals to a to x equals to b connects a comma f of a to b comma f of b. All right? So like it's easy enough to draw a picture of that, right? If this is the function, the graph of the function, right? And this is a point, and this is another point. Then the secant line just connects the dots. Right? I'll use S a comma b of x just for the sake of, let me not even do that. Let me not come up with yet another name for this thing. What's the equation of the secant line? See here, we need to know the 2-point formula for the line. What's the 2-point formula for a line? Let me just sidebar, right? If you want the equation of a line that goes from 2, 3 to minus 1, 10, right? If you want the equation of a line that goes through those 2 points, you can just write it down with the 2-point formula for the line. What you do is you write y is 10 plus a particular number we call the slope, right? Times what? X plus 1. I'm using 10 as the sort of the base point for the formula. What's the slope? It's the rise over the run, right? So in this case, it should be 10 minus 3, which is 7, over minus 1 minus 2, which is minus 3, right? So this equation right here would give you a line which goes through those 2 points, right? But we can just as well do it between the pair a comma f of a and b comma f of b, and that will be the secant line through those 2 points. So the equation of the secant line, by the same token, is this: y equals to f of b. Well, let's see here. I guess I'll use a. I'm going to use a. F of a plus parentheses f of b minus f of a over b minus a times x minus a. The thing in the big parentheses is what we would call the slope of the secant line, right? This right here, the slope of secant line. Now, how is this secant line related to that tangent line we're trying to describe? Can you tell me? Secant's 2 points, tangent's 1 point. That's true. How are they at all related? Like, let's for the sake of this discussion, we're imagining that A is glued in place, like A is stuck, all right? But this B we can slide around, right? what happens if we move b over to here? We get that line, right? So if we move b to there, we get that, right? What happens if we move b to here? Still gluing b and a in place. And we got this line, right? And if you look at that, if we just keep sliding b closer and closer to a, what are we doing? We're getting that tangent line that we're interested in, right? So to get the tangent line, we need to think about sliding b over to a like that. And that will make the secant line become the tangent line, right? So as a, you know, let's see here if I can write. I need to. Well, I'm going to go over here since I don't need this or that anymore. So apparently, we want m to equal, you know, well, I'll call it the limit as b goes to a of f of b minus f of a over b minus a. So the tangent line has slope which is the limit of the secant line slopes. That's almost appropriate. See, the thing is, I don't need an extended warranty on my car. I don't currently own one. I certainly don't need to extend it, but that's what it's going to be about. It's like these people trying to sell me an extended warranty on my car all the time. Anyway, it used to be timeshares, but so what is this limit that I just introduced this concept of limit? What do I mean by limit? What is this? How does this limit work? What does it have to mean? What are the features of limit? You know, I write b goes to a, so a is approximately equal to b in the limit. But, so you're like, well, a is approximately equal to b. What do you mean by that? I mean, we're letting b approach a. But there's a subtle point here, which is the whole reason I'm giving this as a starting talk with you guys, is I want to draw your attention to the fact that there's something we can't allow, at least in our basic concept of limit. So like the whole point of the limit, in part, is to address this problem. Like limits were invented to understand this problem of tangents, all right? What can't we do? Like what's game over for this formula? If you let a and b actually touch, right? If you let a equal to b, that we cannot do. A is not equal to b inside this limiting process. So however we define the limit, it should consider points close to the limit point, but not actually equal to the limit point. That is essential if we're going to avoid the problem of division by zero as we apply the limit to calculate the slope of the tangent line. See that? So when you guys are little, did you ever play a game with your friends like, I'm not touching you, does this bug you? A bit like, I come up to him, like, I'm not touching you, does this bother you? Like that, just over and over again. Limits are kind of like that. Like they don't actually poke, but they come as close as you possibly. So, yeah, that's what a limit is. It's very, very close, and yet not equal to. And that's actually very important because that means that the limit is something past what we can just do with algebra, right? With algebra, we can plug in a number. We can evaluate a polynomial or function or whatever. We can see what the value comes out to, right? With this, we can't just evaluate the slope of the secant line at a equals to b because it's not defined, right? Okay, so that's what we want for the limit. So just to move on with things here. Definition. P in the domain of f. Is it? Okay, got it. So this is notation. This funny looking E means element of, all right? This is the domain of a function, all right? So P is an element of the domain of function is a, oh man, I lived a good life. It's gone now. Is a limit point if there exist infinitely many points in domain of f near P, not including P. Now that's kind of a clunky way of saying it. Let's see, another way I could say that is, let me just throw out some notation here. Definition, the ball of radius epsilon centered at the point P, what that's going to be is we go P minus epsilon to P plus epsilon. So on the number line, what that is just like a little open set, which is open interval centered around P. So like if I draw the number line, this thing looks like this, right? So what if I wanted to, so this is the open ball of radius epsilon centered at P. Open ball of radius epsilon centered at P. What if I want to delete P? What would that look like? And so like the notation I use in my notes is this. B epsilon P sub naught is the same thing, but just like avoiding the point P. So I go P minus epsilon to P, and then I union it with P to P plus epsilon. Let me write that in a different way. So what I'm saying is this is x in the real numbers such that the absolute value, well, 0 is less than the absolute value of x minus P is less than epsilon. So this is the deleted open ball. Centered at P. And so I think that is the thing we need to like define the limit point sort of carefully. To say that it's a limit point means that every deleted open ball centered at P intersects the domain. Which is just like, it's just kind of a fancy way of saying that if we're close to the limit point, there's infinitely many points in the domain of the function, all right? So if you already understand that, that's fine. But, you know, limit point would mean the domain of f intersect the ball of radius epsilon at P deleted is not empty for all epsilon greater than 0. So this is like a sort of more careful definition of limit point right there. All right, well, I'm sorry I have to go through this, but I'm trying to be careful, all right? So the reason I'm just spending a minute or two trying to confuse you, and I don't mean to, but I know what I'm doing probably is confusing some of you because you're not comfortable with the notation I'm using, right? I'm using this funny looking E. I'm using element of, right? Don't be scared. It's just me saying this is the way to carefully characterize a point at which we can take a limit. All right? So if we have such a point, we can take a limit because we have values close to the point which we can consider values of the function, right? And this limiting process, whatever it is, it has to consider like all values of the function near the limit point. So this definition gives me a way of saying concretely, hey, here's a function, its domain has a point where you've got lots of values of the function defined near the point. So here it is. Definition. If the deleted ball of, well, if there exists epsilon, well, let's say eta, greater than 0, such that the ball of radius eta centered at P, instead of using P, I'm going to use A at this point, A, such that the deleted open ball centered at A is a subset of the domain of F. Then we say the limit as x goes to A of f of x is equal to L if and only if all right, for each epsilon greater than 0, there exists delta greater than 0 for which x in the reals with 0 less than f value of x minus a less than delta implies the absolute value of f of x minus L is less than epsilon. You know, writing with a piece of chalk this short makes your hand start to spasm. It's bad. This is the dreaded but lauded epsilon-delta definition of the limit. All right. This is the careful definition of the double-sided limit. All right. This is what we mean by this heuristic thing I was telling you, motivated by the tangent line, right? And so you might say, oh, well, who invented calculus? Well, I mean, who studied tangents? I think it was, man, I remember his name is Isaac Barrow. Well, the teacher of Newton studied tangents, but he didn't quite discover calculus. Before Newton, about 50 years or so, people discovered decimal expansions for real numbers. And before that time, maybe we had rational numbers, right? But if you ever try to just do all your calculations using rational numbers, it's not easy. But decimal numbers, decimal expansions, like you can pretty much be as precise as you want to be, just keep more digits, right? That was a relatively recent invention at the time of Newton, but he had that to use with, right? So he had the number system he needed to do calculations of arbitrary precision. And that's part of what helped him discover calculus. And about the same time, Leibniz, you know, we're talking 17th century, discovered calculus. And they both had some idea of this limiting process, right? But neither one of them wrote this definition down. In fact, mathematicians did very vague, fuzzy stuff for about 150 years before Cauchy and then Bolzano and then ultimately Weierstrass wrote this definition down carefully. And about the time of the Civil War for us, about 1860 or so, 1870, somewhere in there. So this is like 150 years after calculus is invented, right? So it's possible to understand calculus without understanding this. I'm sharing it with you because we'll use this definition to prove limit law properties next class. And then once we have all those limit law properties, then we'll just use those to calculate limits, right? But, so just to let you know, like, you're like, why are you teaching that if that's not going to be exactly on the test? Well, I try to explain things as deeply as I can in here, and then I give you homework which will help you understand more precisely what I'll actually test on, right? And I think it's important that you see proofs of things in math classes. But we'll also spend a lot of time showing how to do calculations. So like the next class, I will use this definition to prove the limit laws, right? And we'll start looking at how to actually calculate some limits. How do you actually calculate limits? It's actually mostly algebra, but it's algebra subject to the condition A not equal to B, right? So it's algebra with strings attached. So I hope I've convinced you that it's interesting. If not, I'm sorry. But anyway, we'll start here next class. So thanks, guys.